Greetings students, and welcome to the Theory of Machines module MOM3602. This is a video presentation of the solutions to assignment number 1, which you should have done by now, hopefully. Let's get started. So there were 4 questions, I believe, in the assignment. We'll go through them sequentially, and in terms of the mark scheme, I will probably give 20 marks per question, and obviously you'll get a total at the end of the day. So the first question is taken from the prescribed textbook, Mechanical Vibrations. As I've mentioned, you can either use the Mechanical Vibrations book by Rao, or you can use the Hannah and Stevens book, whichever one that you have. So the official textbook is mainly for vibrations, and it's written by an author, Professor Rao, and he's from the College of Engineering at the University of Miami. As I say, you do not need to own a copy of the textbook for the assignment, because all of the questions are self-contained, and I did post copies of the questions in the tutorial letter and on the website as well. So let's get started. Give brief answers to each of the following sub-questions and then take it from there. Question number 1 is suggest a method for determining the damping constant of a highly damped vibrating system that uses viscous damping. So essentially, the main learning objective that you need to know in the course is that many vibration systems have a mass, a spring, and a damper. And essentially, vibrating systems are modifications of this basic equation. M is mass, x dot dot is an acceleration, c is a damping constant, x dot is a velocity, k is a spring constant, x is displacement. So when the system has this equation of motion, we make the assumption that the mass and the spring are known, and the question is basically asking us how would we work out c if that is the governing equation of motion. We know m, we know k, and we need to find a way to work out c. The answer is basically you take the underlying equation of motion, you make a perturbation. A perturbation is basically a disturbance in the system. So you allow the system to be disturbed. The system will then have some equation of motion. We analyze the equation of motion in terms of the resultant displacement. So suppose there's a mass, a spring, and a damper. It has a known mass, 2 kilograms, a known spring constant, let's say 1000 Newton per meter, and we would like to know what C is. So we have the mass, the spring, and the damper. We cause a disturbance in the system. Essentially, we bump the system, or the mass, or the spring. The system oscillates. We analyze the motions, and then basically, from an analysis of the motions, we can, in inverted commas, work backwards to figure out what would be the required damping constant C in order to derive this, in order to exhibit this type of motion. So that's basically the approach for determining spring constants when you have a known mass and a known spring constant, and you would like to work out the damping value C. So the second part is basically observe the resulting vibrations and then use this to figure out what C is. The second question is, when in problems where there are free vibrations of undamped translational systems where the equation of motion is the form mx dot dot plus kx is equal to 0, explain if you can apply these results to systems where the restoring force is not proportional to the displacement, that is, to situations where k is not constant. So let's take a moment and look at the equation of motion. The equation of motion reads mx dot dot plus kx is equal to 0. So intuitively, this is a mass spring system. There's no damping value in this particular system. So the question is, can we use that equation where the restoring force is not proportional to the displacement? Look at the term kx. That is basically the equation where there is a proportional force to the displacement. So if the restoring force is proportional to the displacement, F is proportional to X, K would be a constant of proportionality. So, if the restoring force was not proportional to the displacement, that means we would not be able to use the equation F is equal to Kx, or in other words, F retarding is equal to minus Kx. So if the restoring force is not proportional to the displacement, F is not proportional to X, therefore F is not equal to Kx. So the answer is no, it is not possible to do this. If the restoring force was proportional to the displacement, then we'd have F restoring is proportional to X, and then K would be a constant of proportionality. The way of understanding how a constant of proportionality works is to suppose there is a force F1 and there's a displacement X1, and then there's a force F2 and there's a displacement X2. So if we take the ratio F1 over X1, it should equal to F2 over X2. And that's basically the trick we use to work out constants of proportionality. Moving on to question 3. The question states, state the parameters corresponding to mass, linear damping constant C, linear spring constant K, and translational displacement X for torsional systems. So let's go back to the underlying equation of motion. We see at the top of the page, the equation is mx dot dot plus cx dot plus kx is equal to 0. We can rearrange that equation as mx dot dot is equal to minus cx dot minus kx. In this equation is the translational motion. So for the translational motion, m is the mass, x dot dot is the acceleration, c is the viscous damping coefficient, x dot is the velocity, kx is a spring constant, and x is a displacement. So the question is basically asking, what are the analogies to that equation when we have a rotational system? Okay, we have the same basic equation, a constant times the double derivative, plus some other constant times the first derivative, plus some other constant times the x value is equal to 0. So for the general equation for a torsional system, it will be exactly the same. It's just that x will be replaced by theta. So when we have the equation m equivalent, that will be a rotational moment of inertia. C equivalent will be a rotational damping constant. Let's just call it CT, with the subscript T stands for torsion. And K equivalent will be some sort of rotational damping, rotational spring constant. Let's just call it KT. And then finally, theta will be a rotational angle, basically a displacement. And then the next part of the question states, what effect does a decrease in mass have on the frequency of the system? In other words, if you have m is equal to 2 kilograms and then m goes down to 1.73 kilograms, what effect does it have on the frequency of the system, how the system oscillates? When you say frequency, it is typically in the units of hertz. Sometimes you have angular frequencies. The relationship between angular frequency and a normal frequency is basically omega is equal to 2 pi f. You must remember the equation, omega is equal to the square root of k over m. So if omega is equal to the square root of k over m, and k is a constant, and m is getting smaller, that will basically mean that omega n will get larger. In other words, look at it this way. If omega n is equal to the square root of k over m, that's equal to the square root of k divided by the square root of m using basic algebra. The square root of k is a constant. It's not changing. M is going to change. So, for example, the square root of 4 is 2. And the square root of 2 is 1.4. So 1.4 is smaller than 2. So if you divide that by, if you take the reciprocal of that, then that would mean omega n will get larger. Okay, then moving on, the question asks, why does the amplitude of free vibration gradually diminish in practical systems? So the question is, you have some sort of physical system, there's a mass, a spring, there's a damper, it is perturbed, basically you bump the system, it oscillates in some sort of manner, and eventually the oscillations get smaller and smaller, and the oscillations eventually stop. So the physical reason for that is that real systems always have some sort of physical damping, and the damping effect is called viscous damping typically, and viscous damping basically takes energy out of the system. So the system has some sort of initial energy. Say for the sake of argument, it has initial kinetic energy and potential energy of 10 joules. We perturb the system starts vibrating and oscillating, and eventually the energy will die down to zero because the damper is basically taking energy out of the system. Physically what happens is the kinetic energy, let's say there's a mass, a spring, and a damper, and the mass has some sort of motion. It has a kinetic energy, a half mv squared. There's a potential energy, a half kx squared, if k is a spring constant, and there is some sort of damping energy. It is typically a half cx dot squared. So that term basically, well, it's a finite amount of energy, and as the system oscillates and time goes by, that amount of energy that is being put into the damper is being converted into another form of energy, typically heat, and that energy leaks out of the system. So look at it this way. There's some initial energy, 10 joules. There is a spring, some sort of helical coil. There's a mass, a blob of matter, and there's a damper. The damper is basically a sort of plunger in an oil. The frequency, the motion of the system perturbs the damper. The plunger, piston inside a cylinder, a plunger system, that amount of energy physically moves the damper into the oil, and that kinetic energy is transferred into a mechanical energy, and that mechanical energy disturbs the oil inside the damper, and that basically takes the energy. So the kinetic energy is converted into mechanical energy, which is then converted into heat energy, and the heat energy is basically lost, goes into the oil, and that energy comes out of the system. So the energy of the system gradually gets smaller, and that's basically the physical reason why amplitudes of free vibrations gradually diminish in practical systems. Next question. Why is it important to find the natural frequency of a vibrating system? The question is basically saying, fair enough, you've got this mechanical system, you're doing all of these calculations, why is this physically important? And the answer is that the natural frequency of the system is usually a good indication of the resonance frequency of the system. In other words, if you have some sort of mechanical system, the natural frequency is an indication of how the system would oscillate. In other words, if, for example, you have a bridge and there are soldiers marching on the bridge, this causes disturbances in the bridge. And when the frequency is close to the resonance frequency, the system will basically break itself apart. So it's important to know the natural frequency, because that is something you would like to avoid. Because when the natural frequency is the same as the resonance frequency, that will basically cause problems in the system. And the system will oscillate madly, it'll basically break itself apart, in simple terms. So that is why you would like to know what is the natural frequency of the system. There's a video on YouTube. You can see the link. If you have access to the internet, you would just basically click on that link and you'd watch the video. And that would give you more context as to what a natural frequency of a system is physically all about. And then the next question states, how many arbitrary constants must a solution to a second-order differential equation have, and explain how to determine the value of these constants. Simple answer, you need two arbitrary constants. Without going into too many details, if you have an ODE, a double derivative of something, you integrate it once, there's one constant. You integrate it the second time, there's a second constant. So essentially, when you have an nth order differential equation, in principle there needs to be n constants to uniquely determine a solution to that differential equation. And I think we'll leave it over there. It's intuitively obvious. There are more involved mathematical explanations, but this is an engineering course, and for us, perfectly acceptable to say a first order differential equation needs one constant, and a second order differential equation needs two constants. Then the next question is the frequency of a damped vibration system greater than or smaller than the natural frequency? Remember that we had the term omega n, square root of k over n, and the question is basically asking if omega d is the damped angular frequency of the system, is it greater than or smaller than omega n? So basically we need to determine what is the magnitude of the term square root of 1 minus zeta squared. Typically, zeta would be less than 1, 0.4, 0.6, and so on and so forth. So that would basically give you the answer. The answer is it depends on the magnitude of the damping factor zeta. So if zeta is less than 1, 1 minus the square root of zeta squared is less than 1. In other words, it's less than unity. Therefore, omega d would give you the relative answer. So if zeta is less than 1, let's say it is 0.4. So 0.4 is 4 over 10. 0.4 squared is 16 over 100, which is 0.16. 1 minus 0.16 is some other number that would be less than 1. And if that is less than 1, it would follow that omega d would be less than omega n. Moving on, give two practical examples of a torsional pendulum. So a torsional pendulum is basically something that is oscillating and there's some sort of torsion in the system. So the clock mechanism of anti-clock is a good example. You see the schematic in figure 1, in subfigure A, there's some sort of pendulum, the blob of metal in the wooden frame. It can go back and forth, it's oscillating left and right, and that is basically a torsional pendulum. And then another example would be your dial gauge on your car or machine or some sort of instrument, something that measures a torsion or moment. And that is all we need to talk about over there. Then the next question is, what is the order of equation of motion given by the equation mv dot plus cv is equal to 0? Now, this is a bit of a trick question. Why is it a trick question? If I assume v is some parameter, whatever it is, I have m v dot plus cv is equal to 0. If v is a primitive variable, then it's a first order differential equation. So it is technically a first order ODE because it's a first derivative. Alternatively, if v is the velocity, where the velocity is a derivative of displacement, in other words, velocity is dx dt, then substituting that, you would have a second order differential equation. So this is a trick question. You have to identify, is it implicitly a second order differential equation, or is it mathematically simply a first order equation? So you would get the right answer either way. This is because it's a trick question. Okay. Moving on to question 2, there is a physical system. There is basically a type of rod which is in a horizontal configuration. There is a supporting spring, there's a mass at the end, there's another spring, there are some distances A, B and L. And the question is from the textbook on page 216, and essentially when you have this type of problem, solve for the equation of motion. So the question is asking, please find the natural frequency of the above system when the spring K1 is present and when both springs are present and one spring is not present. So how do we analyze the system? The simplest way of analyzing it is to assume both springs are present, and in the particular case where one spring is absent, simply set that spring to be 0 and then see what happens. Okay, so we're going to consider the general case where K1 is not 0 and K2 is not 0. We have the spring, it's rotating, or is it being displaced? Assume the bar is allowed to rotate at the point on the wall by an angle, and that theta, the angle of rotation, be positive in the anti-clockwise direction. So typically x would be positive in the horizontal direction, y would be positive in the upwards direction, and theta would be positive in the anti-clockwise direction. So let's consider the influence of the spring K1 on the system. If the bar is rotating by an angle theta, then using our previous trick where angle is arc length over distance, therefore the arc length is a radius times the angle, we find that the vertical deflection of the spring K1 in an upwards direction would be the radius A times the angle theta. Therefore, delta K1 is equal to radius A times theta. Now, it's a spring. The retarding force is minus the spring constant times the deflection of the spring. Therefore, the retarding force would be minus K1 times delta. And we would then say, okay, there is a spring. I'm assuming theta is positive. Therefore, this is going to stretch the spring in an upwards direction. The retarding force would be in the opposite direction. There's this retarding force. The force times the distance will give me a moment, or torque. So the torque is R times F, which would be the distance, times the force, the moment arm, times the force. That would give you minus K1 A squared theta. We would apply the same reasoning to the other spring K2. The retarding force, if this is theta is positive, that will be anti-clockwise. It would then squash the spring. If theta is negative, rotation will be clockwise. It will stretch the spring. We don't really care. The sign convention is implicit. This is the radius arm. This is the point of application. Exactly the same reasoning. The deflection of the spring is radius arm times the angle. The retarding force is minus the spring constant times the deflection. Follow through, we get an answer exactly as it is over there. Now, here's a slightly more involved part of the problem. What do we do about gravity? Implicitly, gravity is over there. We assume gravity is acting downwards, and that would have some sort of effect in there. Do we disregard gravity? The answer is yes. Why do we disregard gravity? We assume there is some sort of horizontal motion, gravity impacted on the system, it allowed it to oscillate, and there was some equilibrium. So pretend, for example, the bar is not exactly horizontal, it was some little angle, it's initially in equilibrium, so there's some steady state. When we do vibration problems, we analyze the motion about the point of equilibrium. In other words, this is why we disregard weight unless there's a very good reason not to disregard the weight. Because the effect of gravity will introduce a constant force. Vibrations is the analysis of oscillations about points of equilibrium. As a result, the net torque on the system, in other words, we're going to basically ignore gravity because we implicitly accounted for it when it reached the equilibrium point. The resultant torque is basically the algebraic sum, vector superposition of all the torques on the system. We get this particular expression. We're basically going to use Newton's second law of motion. F is equal to ma. The rotational form of that is torr resultant is I equivalent times angular acceleration. We then calculate the moment of inertias. Over there is an additional explanation in the prescribed textbook. If you don't have the prescribed textbook, it's not a problem. You can look at these pictures in the PDF that I'll post onto the website, which you can look at in your own time. This is basically an explanation of why we would disregard gravity. There's the mass, the spring, and the damper. Disregard the damper. The gravity pulls the mass down. It reaches some sort of equilibrium point of view. And then there'll be oscillations about the point of equilibrium. And there are some more explanations about the kinetic energy and the potential energy around that. In any case, moving back to our equation of motion, we have the rod, we have the mass, we have the dampers. We worked out the retarding forces, the retarding torques, the resultant torque. And then we would say, will you please work out the equivalent moment of inertia? What are we doing over here? We say the moment of inertia is the summation of the moment of inertia of the bar and the point. We're assuming the bar has some sort of mass, the point mass is non-zero. Therefore, we will just do the summation of that. For the moment of inertia of a bar about the center point, it is 112 ml squared. About the end point, 1/3 ml squared. You need to remember this formula. The point is mass times the distance squared. We just add it up. We apply Newton's second law. F is equal to ma. Torque resultant is mass times angular acceleration. We then substitute the values. We throw over the values on one side or the other side, so it's a homogeneous equation. A homogeneous equation is where everything is equal to zero. A non-homogeneous equation where there are non-zero terms. In this course, we'll look at mainly free vibrational motions. In the VTech module, we'll look at forced vibrations, where we have mx dot dot plus kx plus cx dot is equal to f of t. In this course, we use homogeneous equations. All of that is equal to zero. We put it into the standard form. M double derivative plus k no derivative is equal to zero. That's basically mx dot dot plus kx is equal to zero. We then have omega n is the square root of k over m. Mx dot plus kx is equal to zero. Omega n square root of k over m. We just put it in algebraic form over there. We don't really need to simplify it. And then we consider the special cases where one spring is zero and the other one is non-zero. We make the observation that this will basically make our life much easier if we consider particular cases from the general case. So if we consider a very general case where the springs are non-zero, we can analyze the equation of motion, and then right at the end we can say, okay, k1 is 0, or k2 is non-zero, whatever the case is. So when we consider the more general case, we essentially make our life easier because we don't have to really derive everything. We just consider it as a special case. And then that's all we need to do. So this is the general case. And then in the special case where k2 is 0, just eliminate it and then just see whatever's left over. And it's as simple as that. This is why we'd like to consider general problems and general solutions. So if we're engineers or technicians or technologists, if we have a very general case, we can consider special cases, and essentially we don't have to do too much work. So that's the reason why we'd like to consider general cases. Alright, we're halfway through the video lecture. We're going on to question 3. Question 3 states, it's adapted again from the textbook. There is a helical spring. It is made of a certain type of wire. The wire has a diameter, little d. It is then worn around a bigger diameter. So pretend, for example, there's some sort of piano wire or brass wire. It has some little diameter d, 2 millimeters or 3 millimeters. There's a block of wood. It has some diameter. We wind the wire around this block of wood, and there are so many helical coils or active coils. and that's basically a helical spring. So we have this particular spring. It has a frequency of vibration of 193 Hertz. How do we measure the frequency of vibration? Basically, we join the spring to some sort of support. Let's suppose we hang the spring from the ceiling and we put a mass and we let the spring fall down. It bumps up and down, it oscillates, and we have a stopwatch. We measure the period of oscillation, and then the frequency is so many oscillations per second. And it's as simple as that. And then we know the spring constant is 4.62 kilonewtons per meter. In this course we use SI units, so it's 4.62 times 10 to the power 3 Newton per meter. So if you don't know what the correct units are, always just go back to F is equal to ma. Newtons is, for F is equal to ma, force is mass times acceleration, so Newton is equal to a kilogram times acceleration would be meter per second squared. The question then says, please determine the wire diameter and the number of coils, assuming that the shear modulus is 79.3 gigapascals and the density is 7,800 kilograms per cubic meter. So we are given that the spring rate and the frequency are specified by these formulas, and then W is the weight of the helical spring and G is the acceleration of gravity. So the question is basically asking us, please find out D and N given this particular information. So we assume that the weight of the spring is mass times gravity, and M is the total mass of the spring for N coils. Density is mass per unit volume, so rho is equal to M over V. If M is a quantity of matter, V is a corresponding volume. So we consider one coil of the spring. Remember, there are various coils wound around that armature. The cross-sectional area, basic first-year stuff, cross-sectional area pi by 4d squared. For one coil, the approximate length is pi times the diameter. Remember that circumference is pi times diameter. So this is what the formula is saying. The length, the circumference around the coil, is pi times diameter. So the volume of one coil is pi by 4d squared times pi d. However, no problem, they're N coils, therefore the total volume is basically the summation of all the individual volumes. And then we apply the definition of density. Rho is equal to mv, therefore m is equal to rho times v. We worked out the volume. We multiply it by the density, that will give us the mass. And then we substitute it into the formulas, and we have k is equal to that expression, and the frequency is equal to that expression. Substitute known information back into the equations. What is the known information? Known information is the frequency, the spring value, the spring constant in SI units. 4.62 times 10 to the power 3 is equal to all of that stuff. Frequency again, all of that stuff. We have two equations and two unknowns. We solve it simultaneously using the usual back substitution approach. We solve the equations, we get an answer, and we take our answer in SI units. That is 2.35 times 10 to the minus 3 meters, which is 2.35 millimeters. Substituted back into the expression, we have so many turns, and our final answer is 2.35 millimeters and about 19.4 turns. So in practical terms, we say, okay, in the factory we want to construct the spring. Just take a wire of 2.5 mil diameter and wind it up about 20 times, and then you'll get your required information. Alright, now we're going to the final question, question number 4. We have a mechanical system. You've seen this type of system before. We'd like to analyze it. What's the main features? We've got a rod, we've got a helical spring, it is rotating by some angle, there's a spring on one side, there's a spring on the other side, there are a few geometry parameters, and we have to work out the equation of motion for the system. Okay, we must find the equation of motion. This is the system. Is there a mass? bit of a trick question. We assume the mass is in the rod. Alright, so if there isn't a point mass, we assume the rod has some finite mass. This is basically the easiest way to analyze the problem. If the rod was massless, technically it wouldn't contribute anything to the moment of inertia. The simplest approach is to assume the mass is m, and right at the end, set m to be 0 and see what happens. And that's how you'd analyze the motion. So we'd apply the same reasoning from the previous question. In question 2 was that physical system. Now there is a helical spring, and there's still the normal springs and the point mass. Remember, we used this approach. We worked out the deflection of the spring, the retarding force, and the torques. Exactly the same approach. If we solved it once, we basically don't need to solve it again. We just need to adapt it and understand how to adapt it and apply it to the current problem. So we've got this rod. It's rotating by some angle theta. It will stretch the spring to cause a retarding force, and the retarding force will then exert a torque on the system. This will stretch the spring. If it goes by an angle theta, it will generate a retarding force. The retarding force times the moment arm will give you a torque. There is a rotation by an angle theta. It's a torsional spring. The torsional resistance is a spring constant times the torsional deflection. So we apply the same reasoning as in the previous problem. Assume theta is positive. It rotates clockwise. The diagram is specifying theta is positive, so we assume that's the sign convention. If the bar rotates by an angle theta, it will stretch the spring by a distance of the moment arm, a times theta. In this case, this distance, which would be L times theta. So we have two springs, K1 and K2. Spring K1 has a moment arm of A. Spring K2 has a moment arm of L. It's a rigid rod, so if the rod deflects by theta, this will also deflect by theta. Fair enough. We work out the retarding forces minus the spring constant times the deflection, and then the retarding torque would be the moment arm times the force. We get some answers. We add it up. It's a vector problem. Torque is a vector as well. Technically, torque is a vector because force is a vector. So A cross F is also a vector. So the torsional spring will generate a resisting torque that is proportional to its angular deflection. This is basically what you must understand and remember. So the resisting torque is minus kt times theta. So this is the underlying equation of motion for a helical spring that is exerting a resisting torque. We apply the principle of vector superposition. We then look at the system. There's a spring K1, there's a retarding force, there's a retarding torque. There's a spring K2, there's a retarding force, there's a retarding torque. So there's a retarding torque of here, there's a retarding torque of here, and there is a retarding torque for the torsional spring. We take the vector superposition of that, we have accounted for the sign convention, we get the resultant torque. Applying Newton's second law, F is equal to ma, or torque resultant is I equivalent times theta dot dot. The question does not specify mass of the bar, it simply states there's a uniform mass per unit length. If it's a one-dimensional problem, the density is defined as mass per unit length. If it is a flat plate, the density is defined as mass per unit area, so many kilograms per meter squared. Physically, how does this work? If you have a wire and you have a density, you have so many kilograms per meter of wire. So to work out the total mass, you just multiply it, multiply the length by the distance, and then it will give you so many kilograms of wire or copper or whatever the case is. If you have a piece of paper in front of you, that technically is a two-dimensional density. So if the flat piece of paper has so many grams per centimeter squared, if you work out the area of the paper and you multiply it by the density per unit area, you'll be able to get a mass in so many grams. So many square centimeters of paper multiplied by density of so many grams per square meter will logically give you a mass. So you can have a one-dimensional density, a two-dimensional density, and a three-dimensional density. So the learning objective is the density is not always a mass per cubic meter. It could be kilograms per meter, or kilograms per square meter, or kilograms per cubic meter. So it depends really on the type of problem that you're looking at. Going back to the system again, the equivalent moment of inertia is 1/3 mass times length squared, because it's fixed at the pivot. So I equivalent is 1/3 ml squared, and then we put our definition of mass per unit length. Rho is mass over length, and then we substitute it, that we get an answer. We apply the rotational form of Newton's second law. F is equal to ma for translational displacements, and for rotations, torque resultant is I equivalent, theta dot dot. We substitute our equations. We then transfer various terms to the other side, so we have a homogeneous equation. So we have m theta dot dot plus k theta is equal to 0. So some constant, some double derivative, plus some other constant, zeroth derivative. Theta is basically the zeroth derivative. So m theta dot dot plus k theta is equal to 0. It's basically a mass spring system. This is basically a mass spring system. It's an equivalent system, to be fair, but it is, at the end of the day, still a mass spring system. And then omega n is equal to the square root of k over m. And it's as simple as that. And that would be the end of the main presentation. Thank you very much for your attention. Okay, here is a very quick explanation of how we would actually numerically solve the differential equations. We have our system over here, and there is a physical system with various geometrical parameters and force components, and we did the derivation using the analysis. And at the end of the day, when we did the analysis, we ended up with a differential equation. In this particular case, it is a second order differential equation. There is a constant m equivalent, double derivative, plus k something is equal to 0. This is her homogeneous equation. In general, there will be a damper value, so there'd be an m, a c, and a k. When we have that equation, we'd like to solve it. So in this particular case, the equation parameters are defined in terms of the bar mass, the point mass, the length, and the various the distances to the springs. So we have the equation, we'd like to solve it and understand how the equation is going to go. In this course, we will not focus on numerical methods. Our focus is mainly on the analytical dynamics side, and as an introduction to vibrations and various other components in the module at a later stage during the year, cams and governors and so on and so forth. So more in terms of advanced material, you would use computer software like MATLAB or Octave or Python. And in this case, I'm going to show you how to run a computer code using GNU Octave. When we start up the program, it gives a screen, and basically we would write some equations over here. For example, we'd like to plot the sine of x and then to plot it, we just say plot There's our graph that we'd like to plot. Obviously, we'll not type the equations in the main command window because that would be a little bit too complicated. and we would like to actually run the computer program from a text file, or what is known as a MATLAB M file. So I've written a computer code to solve the problem. I'm going to run the computer code for the particular problem that we have over here. This is the problem. There is a bar. It is pivoting at a certain point. There is a point mass. The bar has a particular mass. There is an A, a B, and an L, a K1 and a K2. In this case, what we do is we clear all the variables from the main window. We'd like to clear all the variables. There's nothing in the workspace. So we write the computer program, clear all the variables, do some formatting, enter some parameters. Capital M is the mass of the rod, little m is the mass of the point in the end, K1 and K2 are the spring constants. For the sake of argument, I put in various values. When we did the analysis, we ended up with the differential equation, and the differential equation was various things times the double derivative plus various things, zero derivative. So we'd have an M equivalent, a K equivalent. In general, there would also be a C equivalent. In this particular case, C is equal to 0, so we won't worry about it. We then have the equations over there, and then at the end of the day, it is in a differential equation. How do we solve a differential equation? Generally, when we have a differential equation, we have a highest order derivative, and then various lower order derivatives is equal to various component. In this case, it is a homogeneous equation, so everything is equal to 0. In general, it could be a non-homogeneous equation. It could be an introduced force as a function of time. So in this particular case, we write it in terms of these various parameters. And the trick to solve differential equations, at least in engineering dynamics problems, is to set it up as a simultaneous system of differential equations. So basically, if it is an nth order equation, we would then have n equations. So this is a second order equation. We would have two simultaneous differential equations, and the trick is to define the parameters as a derivative of other parameters. So for example, if we have this particular equation, we'd create a new dummy variable y1 as the original variable, and then there'd be a y2, which would be the derivative of the previous dummy variable, and so on and so forth, all the way up to 1 less than the highest order derivative. Then, when we have it in that particular form, we could rearrange it and we'd have a simultaneous system of first order equations. So, in this case, we have the equation M equivalent x dot dot plus C equivalent x dot plus K equivalent x is equal to 0. We then do some tricks with dummy variables y1 and y2 as indicated over here, and basically we then set this up as a simultaneous system of equations. These could be linear equations, these could be nonlinear equations, they could be explicit dependence on time, they could be an implicit dependence on time, it could be arbitrarily complicated. What I will quickly demonstrate is how to use what is known as the Runge-Kutta solver. The Runge-Kutta solver is a built-in function called ODE45 in MATLAB and Octave. So we have our equations, we do some calculations, we set up a function for the differential equations, we put in an initial time, a final time, a number of points for the time increment, and then we basically use the ODE45 solver to solve this particular system of equations. When we solve it, in order to solve it, I would just press the button F5 on my computer. It then changes into the directory where the M file is located. The program is running. and then we get an answer. So let's quickly interpret what the answer is looking like. So this is basically an introduction to numerical simulation of engineering dynamics problems. You'll probably see more of this when you pursue further studies in the BTech. At this point in time, it is not part of the national diploma, and this is more for interest. So don't worry too much about this part of the presentation. This is what comes afterwards when you pursue further studies. In this course, we'll only worry about deriving the equations. We won't worry about solving the equations. You would solve the equations in your BTech module. So we have the equation, the system. In this case, it is a bar. There's some springs. There's a point mass. We solve for the degree of freedom, which is the angle theta. We get some answers. And when we get the answers, I've converted from radians to degrees, so it becomes more obvious. Basically, the bar would then have some initial conditions. In this case, I assume it is an angle of 0 degrees to the horizontal. There is some initial angular velocity in an anti-clockwise direction. And when we do that solution, we have that the bar would increase in angle, go back to 0 degrees, go into negative angles, and so on and so forth. And obviously there would be a corresponding velocity. In this case, I put some initial conditions for the initial position of the bar, which was 0 degrees. I'm converting it to radians, and I assumed an initial angular velocity of 1 degree per second. So this is 1 degree, pi radians is 180 degrees, so I'm converting from degrees to radians. When I do that simulation and solve it, I do get an answer like so. So this is the position. The angle increases, the angle decreases, the velocity increases, the velocity decreases. When we solve it, we can also animate it. It would take maybe a little too much time to show the full animation process, but this is a snapshot of what the animation looks like. So in the course, I demonstrate how to analyze equations using Newton's equations of motion. You derive some equations. You can work out the natural angular frequency, the damping factor, and so on and so forth. So there's a system of differential equations. You would physically solve it on a computer numerically, and this would result in a physical motion at the end of the day. In this case, I simulated it for about half a second using the data. So that is how you would do an actual simulation. Alright, that's the end of the presentation.